Yeah, we never thought 2022 will be like that, but it is. It is like its predecessors. So let's hope it is not too bad.
Really.
Is the classes going on in the usual way or is online?
No, it's online. DK, good morning.
Morning.
So we are having online only. It was planned that we'll have hybrid, and then when it was supposed to start at that time, things were really under. Means it was not under control.
Mhm.
Because we had convocation and the second year also arrived and they were enjoying the convocated batch. So that was the
Spread of, yeah.
Pareshji, is Pavel your student?
yes, he's doing PhD here. He did his MTech, so he's going to present his work.
So I think it would be appropriate if I ask you to introduce the speaker today. Would you be able to do that? Would you be willing to do that?
Yes, I can do, or maybe DK can also do.
Yeah, DK does all the time. Let's let the
Go ahead, Paresh.
supervisor
You
introduce his
you
student.
know
I
him
think it's
best.
an honor.
Okay. I'll.
Yeah.
So you just let me know when I should.
Yeah. So I'll ask you. Okay.
Yes.
So yeah, just giving you heads up in maybe a couple of minutes. Maybe I don't know how many have joined. We have 17 participants. So yeah, it is 9 o'clock. Yeah, we can.
Good start. Maybe this year we'll have more students from Indian schools presenting their work. That will be good.
Yeah, that would be really nice.
The advertisement for those who are joining from India that please share your. This is not a formal review, so if you can share your work, you may get some comments or feedback that may be very useful for your research.
Yes, that's what I told Pavel, that you should go ahead and it's a little unconventional taste in front of the experts. And
I see Dr. Sen is also here. So Pavel, yeah, we have.
Sen, you are in dark. Or you saw put some light. I don't see you. It's looks very dark. Your room.
Oh,
Dr.
Good morning,
Sen
sir.
is
Dark. We don't see
oh,
you.
I'm just getting reflection from sun. So
yeah. Good morning, Dr. Sen.
yeah, good morning.
Good morning, sir. Happy New Year, sir.
Happy New Year. How are you, Paresh?
Fine, sir. So what about you? People are fine.
Good. Yeah, just staying locked up in the house.
Is the UT Austin opening up face to face, Dr. Sen, or online?
Until the end of this month, classes will be all online, and then we'll reevaluate. So, no, actually, we are going to offices in a couple of days a week, and I taught last semester all, basically in person last semester. But this semester, thing, since the cases have gone up, there are some restrictions. So we'll reevaluate end of this month and see if we should. And that. Yeah, I think it's good that you're getting some student presentations from India.
So, I mean, there are some new folks who join. I guess some of them we haven't probably heard. If you can introduce in the meantime, that'll be good.
Yes.
I see Arnav Sarkar, Pratik Saha. This seems like a new names, at least to me. So just say hi. What you guys working on, where you are located, just a basic. Saraswati, Shil. Anyone? Okay, I'm going to ask then someone. Okay, what about Saraswati Shil? Can you guys just say hi and where you are and you are what you do?
I am 2-year MSc student.
Sorry, I missed it. Couldn't hear much.
Am I audible, sir?
Yes, please. Yeah, go ahead.
Hello, sir. This is Shashwati from Kolkata. I'm 2 years MSc geophysics student. I'm in my first year now.
A student at IIT Kharagpur or in Calcutta?
Yes, sir. IIT Kharagpur.
So actually, I feel sometimes bad for the 2 year because they may not have got chance to go to even campus because they are closed for the last 2 years, right? It's very
Yes, sir.
unfortunate
We
because they have
haven't
not
visited.
seen the campus.
Yes, sir. We haven't visited the campus yet.
Well, whenever you get a chance and Kharagpur open up, do go to the campus because this is a really nice campus and see people face to face. Thank you, Saraswati. I see.
Thank you, sir. Thank you.
See some more folks. Of course, Pavel will introduce. What about Arnav and Pratik?
Sir, I am Arnav Sarkar. I am a student of 2-year MSc in geophysics, and I am currently in first year in IIT Kharagpur.
Okay. Thank you. Okay, so starting in 9:04.
Yeah.
Bye. I'll let you get started. Yeah.
Yeah, I think so. We should start. Okay, so welcome to the first talk of this year. Happy New Year, first of all. And I don't know, happy Makar Sankranti. It is still Makar Sankranti here in US. So I'll request Dr. Paresh ji to introduce the speaker for us. Dr. Paresh, please.
Yes, please. Thank you. So I'd like to introduce Mr. Pavel Karmanov. Actually, he came to IIT Kharagpur in the year when I also joined from ISM Dhanbad that time, so 2018 as an MTech student. And Mr. Pavel Karmanov, after that, he completed his MTech in 2020, and then he joined PhD. Of course, he did his MTech thesis with me, and now he's doing PhD with me. So initially, I sent him during his internship period to ONGC to get exposure of this hydrocarbon. So he was doing the MTech here. That is more of a broad course. So he would require more in depth of hydrocarbons. So there he met Dr. Rangarajan, and he also introduced to him this open detect and other things which we have now. So his basic degree, he's from the part of the Russia Chita, which is in Russia, where near Siberia. So he has completed the specialist degree program as here, as you could see. So mainly his main degree is in the geophysics from his country, and of course his father is also a geophysicist, his grandfather is also geophysicist. That is one interesting thing I came to know about him. And he has got a first class or whatever you may say in their way. So he's a good student, and he is a silver medalist also in MTech. So that is one of the best thing I can tell you. So he competed with his counterparts and did very well. So he's very sincere, hardworking, and of course he's getting acquainted with these subjects. So I think for him it's a good platform that you experts can give him a good, critical as well as whatever you may say. So I wish him all the best. So that's all I must say about him.
Thank you, Dr. Paresh. Now I'll request Pavel to please start your talk. Thank you so much.
Yeah, thank you, sir. Good morning and good evening, ladies and gentlemen. Today, I'm going to introduce a new technique, which is called the automatic seismic horizon recognition from seismic data using correlation exponent and its higher order. a case study of Parihaka Field offshore Taranaki Basin, New Zealand. Yes, the aim of this research is identifying the stratigraphic markers by using seismic data in automated mode. And this automation would be achieved through the application of correlation or a scaling exponent and its higher order. The objective of this work is to examine the scaling exponent and its higher order on the synthetic data, and through this way identify the most convenient parameters for the further work, for the main work, and to apply the technique to the post-stack 3D seismic data and estimate the possibility of detection of the main geological features like horizons, faults, bright spot anomalies, etc. Methodology for defining inlines or cross lines and capturing the information seismic from seismic data. We used OpenDetect software. For reading SegWi files and for seismic traces extraction and calculation of scaling exponent and its higher order derivative, we used a code that was written in MATLAB. For define the trace number from inline and crossline numbers, we used a program called SegWi Detective. And for exhibition of the results, for representation of the results, we used a program Surfer 13. Let us talk about automated stratigraphic layer detection using combined scaling exponent and its double derivative or higher order. Let us look through the theory of this method. Let us suppose that there is a length of 30 meters, and we can measure this length through a length scale with 5 meters. Our ruler size is, or length scale, it is 5 meters. And n is the number of length scales to map the length L. So to measure length of 30 meters, we need to use our ruler, our length scale, 6 times 1, 2, 3, 4, 5, and 6. So the number of length scales will be 6. But let us suppose that our length scale will be 6 meters. In this case, we need to measure this length of 30 meters 5 times. 1, 2, 3, 4, 5. And the number of length scales to map the length L will be 5. And what we can observe that with a decrease in the length scale, the number of length scales to measure some kind of length will be increased. And on the contrary, with the increasing of length scale, we can measure the same length with a less number of times. So, and we can conclude that these parameters are inversely proportional. And they, on the screen, you're able to see their relationship because they are reversely proportional. You're able to see C, it is their proportionality constant, and alpha are length scale in the power of alpha, where alpha is the scaling exponent. It is a parameter that we will use in our research. Let us talk about the correlation integral. On the screen, you are able to see the formula of this correlation integral, where n is the number of pairs of digital values of seismic trace. In our case, it was 1,225. So below, you're able to see the formula from which we calculated this number of pairs, where factorials of n and k, and n minus k, where n is the number of events. In our case, it is 50. It will be our length scale or window length. And k is the number of pairs. Our number of pairs is 2. That's why we calculated the number of pairs, 1225. R is the length scale, or further we will call it window length. Rij is the distance between any 2 points of the cluster set obtained using the distance formula, with using time values and amplitude values. And H is the Heaviside step function. It is equal to 0 when Rij less than the length scale, and equal to 1 for Rij more than R. And through this formula, it is possible to bind correlation integral and the length and scaling exponent. They are connected through length scale, and correlation integral is connected with the scaling exponent. And we would like to present another parameters that we will use in our research. It is a double derivative. Below, you are able to see the formula of a double derivative, where we used the values of scaling exponent and the length scales in different points, in points I and j. So let us look through the previous research. The scaling exponent was presented by Grassenberg and Prakashia in 1983 for the first time. Garyanov in 1997 proposed that fractal nature is a universal property of the continent crust. After that, earthquake and microseismicity patterns of underground mines gave the robustness use of the correlation integral technique. Mondal and Roy, Roy and Gupta, and Roy and Pandhi, Roy and Ram. So as you can see, this technique applied for earthquake forecasting, for studying earthquake events. But in our case, we apply this correlation integral technique to a seismic data study for the first time. On this screen, you're able to see the algorithm for calculation, MATLAB algorithm for calculation of scaling exponent and its double derivative. So here we input some seismic trace, segment it in a different window length. It is our ruler size or a length scale. And after that, we look it from I1 to NW. These are a number of windows. Through the work, we compute the R values, the radius range values, and also we compute the correlation integral. After that, we plot it. The program plots it in a logarithmic scale. And finally, the program calculates the slope of the line and store it. And the slope of this line, it will be our scaling exponent value, or multifractal dimension parameter. After that, when all values are calculated in a particular window length, the program saves this scaling exponent value or multifractal dimension parameter and save it through with a time domain for each segment, and calculation process stops. Here you are able to see the algorithm for calculation of radius range. So first, the program calculates absolute difference between all possible pairs in the sample. After that, the program sorts it sorts the distances in ascending order. Next, program selects the optimum levels of radius range between minimum and maximum values. After that, it counts the number of those distances which are less than or equal to radius range level. Repeated for and the program repeats the same work for all selected unit of radius ranges. And finally, program selects the optimum radius range that gives highest change in count. It means the cluster of points. Let us go through the first part of our work. It is a synthetic traces analysis. So in synthetic traces analysis, our objective is measuring of possibility of the automated seismic horizon recognition method to detect a border between two stratigraphic layers. And also we need to define the window length for the further work, define the minimum window length. Our methodology for our work for synthetic data, we used F3 Netherlands 3D seismic data set. It is free available in the internet. It's from available seismic survey, 3D seismic survey. We used it for our synthetic traces analysis. So we interpreted seismic horizons D0, slump, and D4 that were downloaded from the link given by another paper, Silva et al. In 2019. And we used OpenDetect software for viewing and extracting the seismic data. And of course, we used calculation. We used MATLAB code for calculation of scaling exponent and double derivative. And before this, we used a special MATLAB code for extracting of amplitude data from seismic traces. This is our synthetic data. Here you are able to see the main horizons, D0, slump, and D4, and 5 sets of cross lines. Totally, 20. We have studied 25 traces. So I would before presenting the results, I would like to explain you the calculation process. How is it? So on the left side of the screen, you can see the amplitude values from one particular seismic trace. These are time values in milliseconds with a sample interval 4 milliseconds and amplitude values, positive as well as negative. Let us suppose that we have chosen a window length 5. So we take 5 values of amplitude. And for this set of amplitudes, we calculate a scaling exponent. In this case, it will be 4.8, and double derivative value will be 0.014. So we plot it for time for the time that where this window length ends. It will be time 988 milliseconds. So for the end of this window. So SE will be scaling exponent, and DD will be double derivative values. So we repeat the same procedure, window length 5, calculating of scaling exponent and double derivative, and putting these values of scaling exponent and double derivative for the last time value for the end of window length 5. We repeat the same procedure for each set of 5 values of amplitudes. Again and again, we repeat the same procedure. But as you can see, for the last value, there is no value. There is no value of the last set. There is no value of double derivative, because double derivative requires further value of scaling exponent. Further, there is no another value of scaling exponent. That's why double derivative is not calculated. That's why the values we have the amount of double derivatives less than the amount of scaling exponent by 1. Let us go further. We combine all these values of scaling exponent and combine all values of double derivative. That is the logic, that is the sequence how we calculate our parameters. Now let's look through the results. For the cross lines, inline is the same everywhere, but cross lines are different. For the set of cross lines from 300 till 304, we are not able to see a trend of a scaling exponent. And as well as we are not able to see the trend for a double derivative. Why? I think it is because the amplitude values are not extremely high. They are mostly uniform, positive as well as negative. But below, for the set of cross lines 375 till 379, we are able to see a trend. Below, for time value 1088, we are able to see that scaling exponent values become lower than in the upper part. It can be connected, it can be correlated with the increasing of amplitude values at the same time interval, at the same time point, because here we are able to see strong positive amplitudes. So we are able to connect strong amplitudes at one time value at one time interval and a scaling exponent. On the double derivative, we're still not able to see a trend. But let us go further. Results here become more interesting. Here, for interval for the cross lines 450 and 454, we are able to see this zone of low values of scaling exponent. Here you are able to see it, and also you are able to see the transition zone from negative values through the zero values to positive values of double derivative. And it correlates with the increasing of amplitude values. You can see that in the upper part of the set of this set of traces of cross lines, amplitudes are low, positive as well as negative. And here we are able to see the increasing of amplitude values, positive and as well as negative. And this zone of high amplitude values correlates with the zone of low scaling exponent values and with the transition zone from negative to positive values for double derivative. The same we are able to say about the set of cross lines for 522 and 529. The same low scaling exponents, transition zone from negative to positive double derivative, and high amplitude values, positive as well as negative. So we are able to identify horizon slump because it correlates with the high amplitudes. For the set of cross lines 600 and 604, we are able to see the same low scaling, high values of scaling exponent, and are correlated with the zone of low amplitudes, positive as well as negative. And low values of scaling exponent are correlated with the zones, with the zone of high amplitudes, and the same transition zone for double derivative, negative, zero values, and positive. So what kind of conclusion we can do? The zones of the highest amplitude contrast with the most positive and the most negative values correlate with the zones of low scaling exponent values. Here, the high contrast amplitude zone, and here the low scaling exponent values. They are correlated. Next, the zones of low amplitude contrast correlate with the zones of higher scaling exponent values. Here, you are able to see a low contrast amplitude zone. And above these low scaling exponent values, you are able to see higher values of scaling exponent. On the double derivative maps, we can see a transition from negative to positive values with 0 values at the center of the scaling exponent value zones. So at the same time point, low scaling exponent values zone, and it correlates with the transition zone for double derivative. And we have observed that scaling exponent maps with window length 5 show the most acceptable results. And it will be our minimum value, minimum value for window length. Let us go further. We will have a brief introduction to a geology of the study area. Our study area is the Parihaka 3D seismic survey, which locates in the Taranaki Basin offshore in New Zealand. Here, you are able to see the location of this survey and where it is located. So we collected information regarding geology of the study area from Arawa geoseismic section received from Arco Petroleum New Zealand Incorporated. Here, you are able to see the main formations, the main faults, and the well, Arawa 1. So we have found the same signatures in OpenDetect, and that based on the geoseismic section, we did our interpretation. We identified the main faults. It is the Cape Egmont fault zone, giant fault zone, the main formations, and the progradation cliniform unit. So what kind of formation present here in this survey? The first is the giant forceps formation of Pliocene, Pleistocene age, is the thickest housing, is the thickest formation within the seismic survey, which house the paleo channels and progradation clinophores. Next, it is a Urinui formation. This is Urinui formation of late Miocene to early Pliocene. Age is dominantly claystone with interbedded sandstone. Next is the Moki formation. This is the top of Moki formation. This is one. This is the Moki formation of late Miocene. Mostly contains interbedded sandstone, claystone, and tuff. And the last one is Tikarangi formation. This is the top of the Tikarangi formation, and this is the formation itself of Oligocene to early Miocene age. Mostly contains limestones. And let us show you the results that we received. Totally, we have studied three in lines and one cross lines with step 100, and totally 48 traces of the Parihaka 3D seismic log we studied. By using scaling exponent, it was possible to detect different features in 77.3% of cases, and by using double derivative, by 44% of cases. Let us look through the scaling exponent results. So what we can identify is the on the scaling exponent map is the strong anomaly below the bright spot A and below the bright spot B. Also, the lower part of the giant forceps formation, it is the progradation clinoform unit, express the higher values of scaling exponent. And the top of Urinui formation and Moki formations are identified by low values of scaling exponent. I suggest that it is due to higher values of amplitude, positive and negative, on the top of these formations. And the same signature we are able to see on in line 2600. The same very strong anomaly on the zone below the bright spot A, and on the place of the progradation clinoform unit, where this strong anomaly is observed below the bright spot A, but on the place of Tikarangi formation. And we are able to identify the top of Urinui formation and Moki formation. And not directly, but indirectly, we are able to identify the presence of Cape Egmont fault by changing of scaling exponent values. Next, we are on the inline 2510. We are able to see a strong anomaly. It reaches scaling exponent values 20 and even more than 30 in some places on the place of the progradation clinoform unit. Also, the fault zone could be identified not directly, but through changing of shape of the reflectors, by changing of shape of the scaling exponent values. The same, we are able to see the top of the Urinui formation and Moki formation. For cross line 4470, we can see the same very strong anomaly below the bright spot A. Values reach values of scaling exponent become more than 30, and the same the progradation clinoform unit exhibits the higher values of scaling exponent, and the zone of this unit highlights with the strong anomaly. Also, the top of Urinui formation and Moki formations, they are visible. Let us look through the results from received from the study of double derivative. For inline 2657, we are not able to see strong identifiable marks, but we can see the higher values of positive and negative values of double derivative for zones below the bright spots A and B. And on the place of on the top of the Urinui formation, we are able to see the negative values of the double derivative. But for inline 2600, we are able to see the interesting picture. We are able to see the interesting trend. Of course, the values for the zone below the bright spot A shows the high anomaly amplitudes, high anomaly, positive as well as negative. And the progradation clinoform unit appears on the double derivative map by a transition zone from positive values to negative values. It may be, it may be connected with the less compacted sediments for the progradation clinoform unit, and it it is expressed in amplitude and consequently in the scaling exponent and double derivative. But for the inline 2510, the main anomaly we are able to see for the zone under the progradation clinoform unit. It is the brightest anomaly for this map. The progradation clinoform unit reflects as a zone, as a transition zone from very strong positive values of a double derivative to very strong negative values of double derivative. For the cross line of 4470, the main interesting features that we are able to observe, it is the strong amplitudes, positive and negatives, for the zone below the bright spot A. And the progradation cliniform unit zone is expressed by the also by the transition zone from positive through negative zone. And after that, it goes to a positive zone again. So which is a mark that could identify the Urinui formation, the top of the Urinui formation with the high values of amplitudes, positive as well as negative. This is another representation of our results. We took one particular seismic trace with from inline to 1510 and crossline of 4570. We are able to see the same trend. For example, the progradation cliniform unit zone. It shows low values of amplitude, and it expresses very high values of scaling exponent and a very strong transition zone from positive to negative values. So the progradation cliniform unit is very identifiable. Next, when we cross the Urinui formation, we were able to see the very high values of amplitudes, positive and negative, and it correlates with the low values of scaling exponent. After that, amplitude values, they become more flat and not so prominent, not so high, and it express in scaling exponent graphs with the increasing of scaling exponent values. Again, when we cross Moki formation, we see very strong, very high amplitudes. And again, the scaling exponent values become low. And for Tikarangi formation, amplitude values become smaller, and scaling exponent values become higher. And if we see a very strong increase of scaling exponent, of course, or increasing of or decreasing of scaling exponent, of course, it express in double derivative maps with the strong increasing of a strong increasing of a double derivative. And in such case, we are able to see a very positive, very strong positive and negative peaks. But the main idea is when we see small amplitudes, we are able to see high values of scaling exponent. And on the zones of strong amplitudes, high amplitudes, we are able to see low values of scaling exponent. And it's time for making conclusions. So on the scaling exponent maps, it is possible to define borders between stratigraphic layers, loose and dense sediments, because they express different values of amplitudes. And by such way, it is possible to identify the borders between different stratigraphic layers automatically through their amplitudes. On the scaling exponent maps, zones below the bright spots A and B create very strong anomalies. The progradation cliniform unit creates a strong anomaly on the scaling exponent maps and showed transition from positive to negative anomaly on the double derivative maps. It is very strongly identifiable. Faults can be detected, but indirectly by using scaling exponent and double derivative, where I think it is possible to detect faults, but indirectly through shifting of borders in stratigraphic layers and scaling by shifting the negative values of scaling exponent. Scaling exponent can be used for identifying loose and dense sediments on the seismic section, double derivative, and the double derivative identifies well borders between layers. And it identifies the borders as well as strong the increasing or decreasing the scaling exponent values we can see. And about our future plans. We studied this technique, we applied this technique in post-stack 3D seismic data. In the future, we want to apply the same technique for the pre-stack seismic data, pre-stack 3D seismic data. This is our future plan. So thank you for your attention. I finish it.
Thank you, Pavel. Wonderful work, very good presentation, very nice pictures. You had everything was very detailed and very understandable to a person like me who doesn't do much of seismic interpretation. But really a good talk. So you should be proud of you, and so does your professor. So it's a beautiful talk, and I'll request anybody who has questions for Pavel, either unmute yourself and ask directly. If you don't, then please put it in the chat box, and so that we can answer your questions. So anybody, I think Dhananjay was having some suggestions in the back. So Dhananjay, you want to take from here?
I would like the students to interact. Can you go back to the equations you had where you computed the scaling exponent and the derivative? The slide where you had a equation.
Okay. Just 1 minute. Are you able to see my screen? Sorry.
Yes, if you can see the screen. This is the one we had equations, just to see. Just look again.
Sir, do you want to see the result?
No, the equation.
The equation. This is the first equation. This is the this one.
The next one. Yeah, this one. So with the length, are we talking about the vertical length or the horizontal length?
We are studying seismic traces, so we are talking about vertical length.
I'll let others ask. I'll send you an email later on. I will suggest here is to, I'm sure you may already have done it, Pavel, is to compare your attributes with the conventional known attributes. For example, as simple as comparing an envelope that give you the overall energy of the package. Something very simple, very known, established attributes. Then you know what different features you see in your new attributes compared to the conventional attributes. Okay, but it's a good talk, good work, Pavel.
Thank you, sir. All right, so with these new attributes, it is possible to identify high amplitudes and low amplitudes. So as it was said, it is possible to identify dense sediments and loose sediments because they reflect differently with different amplitudes. Also, it is possible to identify stratigraphic layers, but in case when they express high anomalies, when they are identified with the high amplitude values. Also, as you could see that these techniques showed very interesting results with identifying zones below the bright spots, and with the identifying of progradation cliniform unit. Most probably, we can suggest that it is connected with the loose sediments that creates a strong, very low values of amplitudes, and that's why they are detectable in scaling exponent and double derivative maps. So layers between stratigraphic layers, bright spot, and some units that are connected with the progradation marks. These features could be identified.
So anybody else, students, guys, you have any comments? You guys have tried any of these things, and some of you may have already experienced with these kind of attributes. While people are thinking, I will just comment on one more, Pavel. Any times when we compute a derivative, it's very noisy. So did you have any problem with the noise in the derivative attribute?
All right. In different cases, it behaves differently. But there were cases when, for example, there is a border of some layer. It creates a very strong amplitudes, and it could be identified with the double derivative very strongly. So for good results, what I can suggest is to use these both parameters together, both scaling exponent and double derivative. So if one parameter does not show, could not show some proper results, one would show better. So with the double using of these parameters, it will be easier to define features that you are interested in. So in this case, it is good to use both parameters.
DK, as you are saying about this, using some standard attributes like envelope. So when we were doing this for synthetic, somehow we manage with Netherlands data, as the reviewer asked. So can you suggest, or maybe later I'll ask you by email that some data where we can, or some source which we can use as these envelopes and or establish attributes, as you are saying.
Open detect you guys are using. So open detect should have all of these, conventional attributes in the.
Achha, you want me to use those data and just see how it works? Is it?
Yeah, I mean, compare your attributes with the standard attributes, because those are people are familiar with those, how they look, and that way you can show your advantage that with the new attributes I can see some features that I don't see in the conventional maps or attributes volume.
Okay, that's good idea. We may try.
Plus,
that.
I mean, if the Pavel is coding with the MATLAB, just envelope computing is just straightforward, right? I think it's simply called ENV, and then you are done. Or if you want to do more math, compute the Hilbert transform and then compute the envelope. So those are quite straightforward,
Okay, you want just simple standard functions. Okay, I understand that. Okay. Thank you. I could see Amit, maybe he's busy. Amit Padi.
Hello, sir. How are you?
Hello, Amit. How are you?
I'm doing good. Wonderful talk, Pavel. I'm really impressed with how you presented the material. As Sanjay also mentioned, we were able to understand what you taught. It's very important that you get into the teaching mode and you make sure your listeners are understanding, and you did that, and I'm really happy about that.
So, Amit Padi, Pavel, he's IIT Kharagpur when I was here earlier. So he worked with the earthquake. So you have cited his paper, Padi, Roy and Padi. So he's that Amit Padi. So now he's
2007.
Long time back. Now he's doing different or totally petroleum, petrophysics. So nice. You're still in Halliburton, or?
I'm continuing with Halliburton. Yes, correct.
Okay, thank you. So Pavel is doing his PhD now. So we are trying to do for PSTAC data. Let's see how things Because
Yeah.
DK and you people should help us and others. I think Professor Sen was also there. I think he left maybe some.
So he had a meeting, so he had to leave at
Yes.
9:30.
Yeah, I think he left. Yeah.
Yes, yes. Maybe I will ask him later on. He was there for a couple of minutes, maybe.
He said he will watch the YouTube and then
Okay,
give the
yes,
feedback.
yes.
Yeah.
Usually I do that also. I miss, and now I attend regularly, but whichever I miss one between. So I must thank you, Dr. Mahapatra and DK for sending. I'm also trying to circulate among all geophysics and geology students so that they can also come and see how things are going on. So if
The
there's
next
no
time
other,
you can nominate the other students in the group to present
Yes.
his or her work.
Yes,
So in terms of, I guess now nobody asking question, I'm just asking Paresh. This
Yes.
the data you have, Pavel, is a 3D and only post-stack, or you have pre-stack as well?
Actually, now the one which we are using for PhD is only he's having pre-stack, so he's not having both the versions. So that is, and we have only OpenDetect software. So he's
So OpenDetect
facing
is
some.
fine. That if you have a pre-stack, you can always make a post-stack, right? So that's your choice how you want to combine it.
So we did it with this New Zealand data for post-stack, and as you could see his results. So now we are thinking of doing pre-stack. So this is Assam data. So let's see how things work. So we are not still. He's trying to improve the signal to noise ratio, and which you have asked also that you should look for poor signal to noise and see how it works. So what is his relevance, DK and others can say, all these industries still we have such more relevance of this automated, or still, what is your view about this?
I'll just say a few things. For example, so again, Pavel will have to think about how else this can be used as an interpretation tool. So for example, if you are looking for packages, I mean, you have given some geological name to these packages. Of course, these names vary in the different fields. You want to find, can you find these geological sequences or the stratigraphic patterns in using some of your attributes? And any attributes is not sufficient. So you always look for more than one, or more than say 5 attributes, and see which features comes out strongly in one attribute compared to the other attribute. The definition of attribute itself is to do something with the seismic trace, enhance your signal compared to what you don't want to see. Okay, so these are just 1 or 2 attributes, which is not enough. You are also going to try more. For example, standard one plus if you want to do some kind of inversion to come up with a integrated trace or impedance or some kind of inverted volume to see how that look like, not just a reflectivity but as an impedance pattern, because the reflectivity and impedance are too different in terms of the spectral shaping and those. So your attributes might look quite different in the 2 different domains. So just try those. Again, in terms of the data, I thought many university has the Volve data. I don't know if you guys have used it or not.
No, I have not yet. You only told, and
so I gave at least few lines to the student. You also, right, Paresh?
Yes, I have
try
circulated
on those few lines, and I can send you the volume if you need. It's open to all, so it's not secret.
I will do. I will do definitely. I'll ask Pavel. Yes, so we can see.
Pavel, good work. Okay, so keep going. Okay, this is good.
So thank you.
Thank you, sir. I'll try to do my best.
Yeah.
Pavel, again, thank you for presenting. At least you came forward. I'm happy. So I'm happy with the feedback and suggestion. So I must thank all of you, DK and other Amit. So once again, thank you, Dr. Sud, for this opportunity, and Dr. Mahapatra and others. Amit is the vice.
And we are always looking forward to hear from the students from India. It is Pavel, you did a wonderful work, and this presentation was very good, very well done, very detailed. You had everything. You had thought about it, and you had everything and clear to somebody who doesn't understand. Amit also said that. That is very good. So keep doing whatever you are doing, and Dr. Paresh is there. So we are there to help you, and we are really proud of you. You should feel good about it. And good job. Keep doing whatever you're doing. Yeah. And all the best. Yeah. Yeah, I think if we don't have any further, then we can stop the meeting today. It is almost 10 o'clock. I have another meeting.
Yeah.
Okay.
Bye, guys.
Bye.
Yeah.
Thank you.
Bye and
Okay.
good luck. All the best. Thank you.
Happy Makar Sankranti also.
Yeah, happy Makar Sankranti to you all. Yeah, thank you. Bye.
Thank you.